Hello, and welcome to the Dyalog webinar. Today's topic that I'm going to be discussing on the surface might seem a little bit niche and specific, but actually these techniques are quite broadly applicable because of the way that APL handles Boolean data and the way that it can use Boolean data to manipulate other arrays. So today I'm going to be talking about Boolean scans and reductions. I'm going to start by talking a bit about Booleans in the context of APL, and then about scans and reductions, what they are, and the relationship between them, before showing you a couple of specific examples that appear in quite a few use cases. You can find them on quite a lot of the idioms available on Apple Cart, for instance. And then I'm going to just basically point you to a couple of good resources for further reading on the topic. So, without further ado, let's talk about Boolean scans and reductions. So, Boolean data is quite useful in APL. One of the features is that logical values are just the numbers 0 and 1. This is in contrast to some programming languages which have the sort of distinct Boolean data types which might be represented, for example, with the words true and false, but they're different to how numbers are treated. But in APL, logical values are just the numbers 0 and 1, so you can do all the number things with them. So, as I said, they're the results of logical comparisons. So here, for example, we have this 6-row matrix, and that's just giving you the results of each of these 6 comparison functions between this vector on the left and 0. The fact that the logical values are just numbers has been used to create what are these days often referred to as data-driven conditionals. So rather than having to loop through an array explicitly and perhaps use if statements to decide whether to do something with the data or not, with APL, a very common technique is to generate a Boolean array as the result of some comparison, and then use some sort of arithmetic or something to apply your function as a result of the condition. So in this case, we're adding 5% to salaries, which correspond to group A. And this has a couple of advantages. One is sort of that, there are no branching statements, no conditionals, so this statement is inherently parallelizable. Another thing that's quite neat is that in the single line, it somewhat reflects that, plain English language description I gave, right? Salaries increased by 5% where the groups are A, for example. The same idea often comes out instead of arithmetic as a selection, but this shouldn't be a huge surprise. This is quite basic APL. And you can also do some sort of simple statistics. For example, did you know that a third of the alphabet is vowels? Alright, that's a joke, but You can see what I'm getting at here. They're quite useful in lots of different scenarios. Not only are they used in lots of different ways, but their representation or their definitions of Boolean functions in APL is kind of neat to think about. So I'm going to refer now to this vector article by Phil Last called Boolean reductions. And in this article, he's kind of exploring or discussing the pursuit of sort of plain descriptions for the properties of vectors with regards to certain reductions, some Boolean reductions. I'll come back to that much later on. For now, I just want to talk about this table that I think is quite neat. So if you've ever done anything like digital electronics or some other field that uses Boolean algebra, then you might have come across this idea of 16 logical functions for 2 1-bit Boolean inputs. So that's what this table's kind of showing, right? It's if you take all the 4 possibilities of 2-bit inputs to like a logic gate or something, or a logical function, then there are sort of 16 distinct signatures for all the possible outputs. So on the left here we have all those outputs. In the next column is just the decimal representation of these Boolean vectors for each row. Then in the third column, I've taken a bit of liberty here in comparison to the vector article. Although, for a long time, many of these functions are have been representable in APL using, single primitive functions. Not all of them always have been. Well, they still aren't. But these days, with modern operators such as a top and constant, we've just got 1 primitive or 2 or 3 primitive definitions for all of these functions, which is quite neat. There's one caveat worth mentioning, which is just that in Phil Last's paper, a lot of these other functions are defined as defins, and they're also defined in a way where, just like the primitives that have always been this way, they're scalar functions, meaning not only do they map implicitly between values in arrays, but also they pervade down into nested arrays. So each of the values deeply nested in there are affected as well. That's not true for all of the definitions I've given, but I just think they look kind of neat. And then in the last column, I've given a combination of either common names for like digital logic gates, or such as and, or, nor, NAND, right? Or I've given these sort of English mnemonic descriptions of what the function does, which is especially useful, I think, because of the way that dyadic functions work, right? So, you've got greater than described as left but not right. And then you've got left, which is left tack, right but not left, right, which is right tack, etc. Right, so, that's kind of Booleans in APL. Now to the other part of the title, scans and reductions. I just want to give this incredibly brief summary of them. So, reductions are generally functions that summarize something about data. So if you have a vector of data, the reduction will return a single number that tells you some property about that vector, but you lose the details of the information there. And then the scans indicate some kind of progression. So they're like partial reductions along the prefixes of the vector. That will hopefully become a bit more clear as I show some examples. So let's start with 2 quite well-known examples. And reduction asks, are all the bits true? And the related scan, and scan, asks, were they all true so far? So leading ones are all on. As soon as there's the first 0, all bits are off from there. And then OR reduction asks, are any true? Is there even a single on bit? And the related scan asks, were any true so far? So as soon as there's a 1, it's all 1s from there. Or an alternative metaphor is like, as soon as it sees a 1, it spreads that 1 across the rest of the vector. Okay, but they're both, you know, quite well-known scans and reductions. Let's look at some less common ones. After I point out that, in general, the last value of a scan is the result of the related reduction, right? So this is true and starts to paint a picture of, you know, how closely these two things are related, which is kind of obvious, but I'm going to be laboring that point quite a lot today. So yes, let's look at a less common construct. So here's the less than scan, and less than scan has the property of basically leaving the first bit on, and then all subsequent bits are off after the first one. And that's basically because the related reduction is only true if the last bit is the only true bit. So if you want, we can, you know, get a better picture of this by maybe doing the scan a piece at a time, right? So in a scan, the first piece stays, your first element remains basically, so 0, you get a 0. And then you do 0 less than 1. Well, here the last bit in 0, 1 is on, and it's the only on bit, so that reduction returns 1. But then after that, all subsequent reductions along the way all return 0. All right, 1 less than 0, not true. 0 less than 0, also not true, etc. Right, so that's kind of how that relationship works. In terms of example use cases, one that's quite neat to see and easy to explain is marking the beginning of end-of-line comments. So in APL, comments are marked with a lamp symbol, and then, you know, only the first lamp symbol in a line is important. Everything else is part of the comment, so, you know, we can ignore subsequent lamp symbols. Not that you would necessarily have more lamp symbols in comments after that, but you get the idea. All right, that's quite straightforward. And if you were really, you know, interested in the index of the first lamp symbol anyway, you might use index of 1. Might be a bit faster and is generally a bit simpler. Something a little bit more interesting is marking the beginning of groups of similar elements. Right, so in this case we're going to look for where do groups of quads start in this text vector. And in this case we actually need a windowed reduction rather than a scan. So pairwise less than reduce of where the quads are marks the beginning of each of those groups. Right, and that's because that less than reduction is only true going from a 0 to a 1 in that case. Okay, well, let's move on to another example, or another Boolean function. Less than reduce has this sort of interesting property that it only returns true when there's an odd number of 1s in the Boolean vector. So it's the same as like the parity of the count of 1s. What this means for the scan is you have this quite curious behavior where, you know, if you consider the first and the third and the fifth and seventh, etc., 1s as like the odd positioned 1s, and the second and fourth and sixth and eighth, etc., as the even positioned 1s, it joins up odd and even pairs of ones, including the first one, but excluding the second one. We'll see why that, or how that is, and I can also show you in a second how to choose whether to include or exclude both of those. But that's a kind of neat switching property. So let's see. Well, once again, if you go by step through it, 0 is just 0. 0 is not equal to 1, that is true. 1 not equal to 0 is true, and 0 is not equal to that 1, the result there. Remember, we're going right to left within each reduction, even though the scan itself goes left to right. Right, similar output, and then it's not until we get to this 1, so there's now an even number of 1s there, so 1 not equal to 0, that's true. 0 not equal to 1, that's also true. 1 not equal to that 1 is now false, and 0 not equal to that 0 is also false. Hence we get the 0 from there. In terms of use cases, this time, instead of looking at like end of line stuff, now we can start to look at pairs of things, right? So hopefully you might be able to see how this could be useful for extracting quotes from text. So we can just mark where double quotes are in the text vector. And here we're doing not and not equal scan, and that excludes both of the actual quotes, only keeping the text within marked. If you want to include the quotes as well, then it's just the same or not equal scan. So that's kind of neat. And in both of these cases, you should be able to see it's quite straightforward to extract the text either through a compression, or if you want to keep everything separated, you can use partition to create a nested vector of the quoted character vectors. And we could also combine this with what I just showed you before with less than to find the start of each quoted segment, for example. Although I guess you can see this might not be quite as useful as marking the entire portions. But it's still interesting to see how easily you can combine these techniques to do, more and more complex processing. As I sort of mentioned earlier, a lot of the specific constructs I'm looking at here appear in different idioms in Apple Cart, so I just wanted to show you what the extract quoted text idiom looks like in its Apple Cart form. Hopefully, now you can start to understand some of the workings of these things a little bit more. So here's the not and not equal scan, even though in general with Apple Cart, it's there so that you can just search for plain terms, plain English terms, and just copy and paste the idiom, as opposed to remembering all of the individual pieces to construct it every time. Another neat idiom that appears with not equal scan is this one for selecting C style comments. So those appear in languages like Java, JavaScript, and C. And CSS as well, as you can see in this example. I won't go into all the details here. There's some finds, there's some extra reverses and stuff. And in general, if you want to have a more general processor, it does get more and more complicated, and not quite as straightforward as this. But it's still quite neat. Okay, one last example comes from a paper by Steve Jaffe. It's like a series of topics for teaching people who have some basic APL but want to get more intermediate and advanced skills. And in this example, you basically have some data like this, where I guess these letter IDs could be anything really, but I've put them this way to mark three separate fields that are all part of the same table, right? So you've got a field of length 4 containing the A's, you've got a field of length 2 with all the B's, and a field of length 3 with all the C's. And I'll just pop that to one side so we can think about it. But what we want to do is, given the field lengths, for the sake of formatting for a report or something else perhaps, I want to insert 2 blank lines between each of these fields. Now at this point, maybe I should mention that in most of the literature around this topic, Boolean functions does specifically mean a function that takes Boolean arguments and produces Boolean results. But in this case, I'm going to stretch that definition a little bit just to show you this particular example. So given the field lengths, we can have some function which we'll call mTake for multiple take. I won't go into how you make this. You can have a think. There's a couple of good ways. It's basically doing a take of 1 for each of the elements of the argument. So 4 take 1, then 2 take 1, then 3 take 1. And this produces just a partitioning vector for these fields, right? Now, if I want to insert blanks, 2 blank lines between each field, then in modern APL I can use catenate rank 0 to interleave 4, 2, 2, 2, 3, 2, unravel that result, and then do mTake. So now I have a partition vector, but it kind of marks a field and then 2 blanks, and then a field and then 2 blanks, and then a field and then 2 blanks. Then we can use the not equal scan to kind of switch on and off, from field to blanks, field blanks, field blanks, and this becomes an expansion vector for our data. And it's just as straightforward as using the expand primitive on our text matrix. So I like that this is kind of another way of considering that switching on and off property of the not equal scan, as opposed to the previous example is talking about pairing up things. I mean, this is kind of pairing up things too, but it just has a bit of a different flavor about it. So actually, I say that. No, that's the not equal scan. Okay, here's where I wanted to talk about. Sorry, here's where I wanted to talk about a Boolean function that's not exactly a Boolean function. But first, I'll introduce this reference, which is a publication published by STSC, Scientific Timesharing Corporation. Is that right? It's called Boolean Functions and Techniques, and it's a fairly long booklet, I guess, or a small book. And it has loads of really excellent discussion and information, examples, tables, lists upon lists of comparisons of different, things related to Boolean functions and Boolean arrays. But in particular, right now, I want to talk about this page, which it's somewhere about halfway through. I can't remember the exact page right now. But basically, it's about doing partitioned operations, pre-nested arrays. So in modern APLs we have nested arrays. So if you have some vector that's split into fields similar to that previous example, and you want to apply a function to each field independently, these days you can just create the partitions and then apply with each. We'll see that in a second. But prior to that, you had to do something else. Well, earlier in this, the beginning of this sort of book, there is an example, or at least a description of a general partitioned application operator, right, where you take some partition Boolean vector like the one we were generating with mtake, and you can use that along with your argument array, and it will apply a function independently to each of those fields. But it's a sort of loopy solution. I mean, the one written in there actually uses gotos and labels. The one that I'm going to show you in a second uses each, and so for large arrays with lots of partitions, then it gets quite inefficient chasing pointers around and allocating memory. So basically, what they've done is, and I think a large portion of the book is accredited to Bob Smith. His name's not on the front of it, so I don't know if it was just him writing the stuff. Is basically, come up with more efficient, more array-oriented functions to perform this type of partitioned function application, before nested arrays existed. As a result, you do get some speed ups even today. So you'll see that in a second as well. But right now I'm just going to look at a couple of examples to give you a flavor. I'm not going to go through all of this, but we'll look at the partitioned reverse, and we'll look at partitioned plus reduction, although that one in not so much detail. Actually, it might be worth actually mentioning right now that you'll see this n delta, and then in some of the other examples a p delta. That's also just basically it's like a shifted operation, but it's basically equivalent to -2 f/. So here you've taken a minus. Anyway, it's not that important, just something you might want to be aware of if you're interested in the details of this stuff and you go to read it later. Okay, so let's look at this partitioned rotate function. So here's this modern nested array approach, right? It's quite straightforward. You just take your partition vector, you literally partition the array. So here we're separating out the A, B, C, D and the X, Y, Z. I'm going to treat those two independently. We just apply rotate with each and then flatten the result. Right, and you can see that we rotate A, B, C, D, but that all stays at the beginning of the vector, and then we rotate independently X, Y, Z. So the Boolean function that's not really a Boolean function I want to talk about is actually plus scan. This has been used quite a lot in these types of partitioned function application scenarios, because if you take one of these style partition vectors, where a 1 indicates the start of a new partition, then the plus scan gives you sort of ascending integers where the groups of the same integer mark out a partition. So what we can do here is do grade down on that plus scan, and this has the property that because the numbers are overall ascending, it rotates the relative positions of where those indices end up, right? So the indices of the second field end up at the beginning of the downgrade, and the indices of the start end up at the end. However, the order of the individual indices within each field remain intact, right? So it's still ascending 5, 6, 7 and 1, 2, 3, 4. And this means that all we have to do is rotate that vector, and we have indices that produce our desired effect with just indexing. Right, so the first field stays at the beginning, but now the positions of the indices within that field are rotated. So it's pretty neat. I like that it's quite short. It's actually even shorter than that general one. It's not always a surprise, but the page from before, there are some quite long definitions for these types of things. And of course, part of the reason why you might be interested in this even now, when we have nested arrays, is that there's generally performance improvements if you have a bottleneck that involves something like nested arrays, then Boolean scans and reductions and other Boolean techniques can often be a way to find that improved performance. Oh, okay, it's not longer, never mind. Right, so that's our rotate each. Now let's look at a different one. Let's look at the partition plus reduction. You can see that with the nested expression, it follows the exact same pattern in terms of the definition, right? So just use partitioned inclose to partition our data, apply our monadic function with each, and then flatten the result. And in fact, it's such, it's the exact same pattern to the extent that you can easily see how to make a diop out of this. Just replace the function with alpha alpha. So some people are interested in the performance across different data types, so I thought I'd just throw this example in. So here I've got some small integers, some 8-bit integers, then I have some slightly larger 16-bit integers, and then I have some 64-bit floating point numbers, 10,000 of each. And here is the flat array sort of plus scan version of that partition plus reduction. I'm not going through the details of how this works other than to say it's basically, the plus scan is across the entire vector, but then since we care about treating the partitions independently, you basically need to subtract what's been summed up so far as you go along. But anyway, you can see that across these different types, you get a decent performance improvement in terms of the speed. And memory usage definitely improves in all these cases. This star here, this asterisk, denotes that these gave different results, but that's actually just a floating point error propagating through, and the fact that my quad CT is my comparison tolerance is the default 10 to the minus 14. I think this goes away at 10 to the minus 10. But that's something to be aware of, just your friendly reminder to always remember floating point errors. I was supposed to apologize a long time ago. I'm sorry. I'll do it now. Apparently the chat has not been working for this entire time. But I've just been told it's been fixed and it's working now. So if you reload dialog.tv, if you're watching on dialog.tv and you wanted to participate and ask questions in the chat, I hope if you did have any, maybe you wrote them down. But now apparently I think if you refresh the page, the chat should turn up. So hopefully that's okay. Apologies again for those technical difficulties. I will just mention, before I talk about this slide, actually let's just pop back a second, it doesn't hurt. This stuff here, all of these more efficient partitioned function application techniques are now available on Apple Cart as sort of fast versions of, the equivalent partitioned one, like that general partition operator that I showed you here. So I don't know whether it's always a job with Apple Cart to add more synonyms, so maybe in the future it'll be easier and easier to find them, but I expect if you just put the names from either the booklet or you just write partitioned sum, etc., partition reverse, segmented, I've seen as a synonym. Anyway, stuff's on Apple Cart, so you don't have to remember everything or look up everything in a book. We have technology. So part of the reason for some of these speed ups, and certainly the memory efficiencies when it comes to Boolean techniques, comes down to Larry Breed's decision, one of the early implementers of APL. In the very first implementation of APL, it was decided that Booleans should be stored as 1 bit per bit. Some languages store 1 byte per bit, or 1 Boolean bit is represented as a byte. Anyway, with bit Booleans, you have this, all kinds of opportunities for performance improvements, but in particular, you can have what's called single instruction multiple data parallel processing without specific hardware for it, and that's called SWAR, or SIMD without a register. That's basically, if you're storing the bits in a word for 8 bits, or 64 bits in a word on a modern 64-bit computer, then the processor is able to, process words at a time. You have to do some extra fiddling, as far as I'm aware. I don't know loads of the details, but you can get, upwards 8, 32, 64-bit, 64 times speed-ups in particular cases, without any special extra hardware, except modern computers. If you do want to know more about the details of that sort of stuff, there's a fair amount of literature on that topic, so I can recommend, the APL Wiki article on Booleans, which does actually reference this particular title by Bob Benecki. He gave a talk at Dyalog 2016 user meeting, with the same title, A Compendium of SIMD Boolean Array Algorithms in APL. I'm also aware that that talk is the topic of a paper which is still in development, but I think if you ask him real nicely, he might forward you a copy of that. So lastly, I just want to go back to Phil Last's vector article and talk about a little bit about the actual sort of topic of that article. So what that article discusses is this effort to give sort of plain English descriptions for the condition for a Boolean vector to have. A Boolean vector must have some property, and then f reduce omega for some Boolean function f is true. Once again, it gets clearer when you think about some examples, right? So the first 2 examples from earlier, and reduction is true if our Boolean vector is all 1s. Or reduction is true if our Boolean vector has at least 1 1. Then there's the 2 that I looked at in a bit more detail today. So less than reduction is true if the last bit is the only true bit and it's on. Not equal reduction is true if there's an odd number of 1s. And then there's the rest. I've been talking for almost 40 minutes about this stuff, so I'm not going to go through all of these individually. But, if you are interested and if you like this topic and you want to sort of think about it more, it's quite a fun exercise to go through these and try to think about, okay, if this is the property of a Boolean vector such that the reduction is true, then what does that mean about what the scan looks like? And from what I've shown today, hopefully you can see how you would play with those to figure that out. I also want to just comment, like, there's quite a lot of these that have something to do with the odd or parity of the count, so odd or even numbers of 1s. I just thought that was kind of interesting. Right, anyway, that's it for me talking about Boolean scans and reductions. As I said, I've tried to mainly focus on, those that have quite a lot of applications, as in they appear in quite a lot of idioms. In general, they're interesting APL techniques. historically very, very important, but they're also still relevant largely because of potential performance improvements, but also because they appear in a lot of code in a lot of places. If you want to read more about this sort of stuff, as always, the APL Wiki is an excellent resource, getting better all the time. That example I gave with expanding the table, the text matrix of data, comes from Steve Jaff's Topics for a Second course in APL, which is published in a couple of places. I think APL 86 conference, if you have those proceedings, it's in there. But it's also published as part of an APL quote quad, which I think is what that link gives you. Then there's Bob Benecki's Dyalog user meeting 2016 talk, and the related paper, which is in development. No pressure. I'm sorry. Sorry for calling you out like that. Phil Last's article, which was kind of one of the first things I was reading around this topic, and as you can tell, largely inspired a lot of the content, and also the STSC Boolean functions and techniques, which is available from sudleyplace.com. Maybe Adam will probably type that in the chat. Sudleyplace.com. He probably got that from the chat. It was one of you told him. Oh no, he said that before about the chat being before he said about the chat being fixed. I'm waffling now, but partially so that you have an opportunity to ask any last questions, because hopefully you can tell we're reaching the end. So while I wait for any questions about any of this stuff, then I'll also take a moment to do some promotions. So going from furthest in the future from now to nearest, we start with the next webinar in 4 weeks' time. It's Adam. He's back here on Dyalog.tv doing the second part in a series on error handling, which is a fairly involved topic, which is why we've started, with the basics and are moving on from there. That's in 4 weeks on Thursday the 15th of April. It's 4 o'clock again in the UK, but I think the clock's changed between now and then, so that's something to be aware of. Then in 2 weeks' time, is Appleseeds 21. So this is the first of this type of online user meeting we're hosting, which is, although today's topic is largely, people who already know some APL but want to be aware of more intermediate and advanced techniques, this is obviously, more targeting possibly people who might not have used APL before at all. However, I think the content will be interesting to anyone of any APL experience, just from my knowledge of the people who are talking and what they're going to be talking about. But you can find more information about that from the Dyalog website, and you also, if you want to attend, need to register. It's being held using Zoom, but please register to make sure that you can have a place to attend and get the links and such. That's in 2 weeks' time on Wednesday the 31st of March, and indeed the clocks change before then in the UK, so that's 2 p.m. UK time. It's UTC +1. And we're also going to be having a kind of informal Zoom meetup afterwards, sort of a chill chat, talk about APL stuff, for those who are still alive and awake after that afternoon. And then next week is another open session with the British APL Association. On Zoom, you can go to their website, britishaplassociation.org, to find the details of how to join in with that stuff. I've just been told, that's probably confirmation from Bob that he sent me his paper. So if you want it, you can ask me instead of bothering him. So I guess that's payback. But yes, feel free to ask me for any of these references, and I'll try and link you to them somehow. But I'm not officially a distributor, so I do that for all of these things officially. One other point I have been reminded of, unfortunately, due to some last minute changes, I wasn't able to get this ready for right now, but I'm intending to take the content of this and make it a Jupyter Notebook on the Dyalog Jupyter Notebooks GitHub repository, which you can find if you just do an internet search for Dyalog Jupyter Notebooks. Just FYI, if you're interested in that sort of thing, or you want to be able to read this, you know, not as a PowerPoint presentation later, I think I should be able to publish that tomorrow. I'm just going to give it, you know, another minute, just in case, but I don't think as much in terms of questions. So I will just say thank you very much for watching. Hope you found some of this interesting and or useful. And as I've already said, see you in 4 weeks for the next webinar. I'll probably be manning the chat. 15th of April? Ooh, maybe. In 2 weeks at the Appleseeds user meeting, and in 1 week at the British APL Association meetup. All right. Thanks very much. Goodbye.